Okay, let's have a look at Brønsted-Lowry acids and bases. So what is it? Brønsted-Lowry theory is one of several classification systems for explaining the behaviour of acids and bases. Why is it called Brønsted-Lowry theory? Well, it's named after the scientists who kind of came up with the idea at similar times. Johannes Brønsted, I think, is Danish, and Thomas Lowry was an English chemist. So the central concept here that's going to be important for understanding the rest of this is that the Brønsted-Lowry theory talks about acids and bases in terms of the transfer of H plus ions. And you'll see in brackets here that when we're talking about H plus ions, we are also technically talking about protons. And why is that? Why can we use those two terms interchangeably? Well, if I take a hydrogen atom, and specifically we'll take the most common isotope of hydrogen, which is hydrogen 1. Let's draw a little diagram of that. Here we find that it's got one proton and one electron. So in order to turn that into an H plus ion, I need to remove one electron, and when I do that, I am left with simply a proton. So for that reason, when we're talking about H plus ions, we can also use the term proton interchangeably. And you'll need to be able to recognise both of those terms mean the same thing. So the key point here to note, we need to remember a positive hydrogen ion, H+, is exactly the same thing as a proton. So let's have a look at some definitions from Brønsted-Lowry theory. First of all, a Brønsted-Lowry acid is defined as a proton donor, or an H+ donor, and a base, conversely, is defined as a proton acceptor. So all that means, a donor means something is going to give protons to another species, and an acceptor is going to gain a proton from another species. And notice that we're just talking about a single proton here, or a single H+. So let's have a look at some examples then and see if we can identify Brønsted-Lowry acids and Brønsted-Lowry bases. So the first example, let's take ammonia gas, react it with hydrogen chloride gas, and we find that we produce a white solid, which is ammonium chloride. Now it's a little bit confusing here. We've only formed one thing in my products. So before we try and identify which of my reactants is an acid and which a base, it's worth just drawing the two ions that form ammonium chloride, which are the following. So it's made up of an ammonium ion and a chloride ion. So doing that, I can see immediately, well, what's happened to my NH3. It seems to have gained a hydrogen and a positive charge. So in that case, it must have accepted or gained a proton from the other species. For that reason, I can define my ammonia as a Brønsted-Lowry base. It's gained an H+ and become NH4+. So that must mean that my other reactant, which is the hydrogen chloride here, must have donated an H+. How do I know that? Well, if I look at what's produced on the right, I've got just a chloride ion, which has obviously lost an H+. Therefore, I can define the HCl in this case as a Brønsted-Lowry acid. And to deepen our understanding a little bit further, let's just draw a Lewis diagram for each of those species. It's going to look something like that. We've got ammonia, hydrogen chloride, and then the two ions found in ammonium chloride. So what technically has happened in this process? Well, there's two curly arrows to help show what's actually going on. The first curly arrow, this one here, is representing the ammonia using a lone pair of electrons to steal or take that H+ from the hydrogen chloride. The second arrow, which is over here, shows that both electrons from that hydrogen-chlorine bond have returned to the chlorine. Now, one of those belonged to the chlorine in the first place. The other electron, which has come from the hydrogen, has also been gained by the chlorine. Hence, on the right-hand side, we've ended up with a chloride ion, a negative chloride ion to be specific. So what are the key points that we need to recognise from this? Firstly, a Brønsted-Lowry base, like ammonia in this example, always uses a lone pair of electrons to gain or accept an H+. And a Brønsted-Lowry acid, in order to donate an H+, well, it must have a hydrogen atom in it. So you'll notice if you look at a list of Brønsted-Lowry acids, they all contain hydrogen atoms. Right, let's take this a little bit further with a second example. And in this case, we're going to look at the reaction that occurs when I dissolve hydrogen chloride in water. So what do we form? Well, we form these two things. The first one, which you may not have seen before, this H3O plus ion, is known as the hydroxonium ion. It's also sometimes called the oxonium ion. There's a couple of words that a couple of terms we can use to describe it. They all mean the same thing. So in this process, dissolving HCl in water, what's acted as a Brønsted-Lowry acid? What's acted as a base? Well, we need to identify first which thing has gained an H+, and if I compare water on the left and the hydroxonium ion on the right, I can see that my water must have gained an H+. So for that reason, if it's gained a proton, we're going to call it a Brønsted-Lowry base. And what about the other thing? Well, we started with hydrogen chloride. We've ended up with just a chloride ion, so my HCl has lost or donated an H+. That's the definition of a Brønsted-Lowry acid, so that must be a Brønsted-Lowry acid. Of course, when HCl is dissolved in solution, we call it hydrochloric acid, so there's a bit of a clue in the name there. Again, let's draw a Lewis diagram and just have a look at exactly what's going on in that solution. So there's my Lewis formulas for each of my structures. Let's use some curly arrows to show the actual movement of electrons here. And this time we said our water is the Brønsted-Lowry base, and you can see that top yellow arrow is showing that the water is again using a lone pair of electrons to take an H+ from the other species. The second arrow shows the two electrons from that hydrogen-chlorine bond. They've both gone back to the chlorine. Again, one electron belonged to the chlorine in the first place, so it's also gained the electron from the hydrogen, which is why we end up with that chloride ion on the right. So what are the key points here? Well, a bit of repetition for us. First of all, my Brønsted-Lowry base, again, has used a lone pair of electrons to accept an H+. And again, my Brønsted-Lowry acid, we know must have a hydrogen atom, otherwise it couldn't act as a Brønsted-Lowry acid. Now there's a third point here, which is going to be useful as you continue through this topic. Note that always, when I dissolve a Brønsted-Lowry acid in water, we always form that slightly strange thing, H3O plus, or the hydroxonium ion. And because this is always the case in aqueous solutions, we can actually simplify that equation by removing water from both sides. So if I do that, I end up with, well, no water on the left, and if I take an H2O away from my hydroxonium ion, I'm left simply with H+. And this is just a simpler way of expressing that same equation at the top of the page. It just saves us writing lots of H2Os. But the key point here is that if ever I see H+ in aqueous solution, that is actually always exactly the same thing as H3O plus, my hydroxonium ion. Why is that? Well, an H+ is a pretty juicy target floating around in a solution where there's lots of water molecules. So one of those water molecules is always going to snap it up, acting as a Brønsted-Lowry base to form the hydroxonium ion. Okay, let's look at a third and final example. So in this case, let's take a Brønsted-Lowry base and see what happens when we dissolve that into water. So let's take ammonia, same thing we used in our first example, react it with water, and in this case, what do we form in solution? Well, I form the ammonium ion and hydroxide ion. And hydroxide ion, again, is going to be quite important because whenever I dissolve a Brønsted-Lowry base in water, we always produce hydroxide ions. So let's try and identify the Brønsted-Lowry acid and Brønsted-Lowry base. Well, what's happened to my ammonia from the left side to the right side? It looks like it's gained an H+, it's gained a proton. Therefore, it must be defined as a Brønsted-Lowry base. What's happened to my water here? Well, water on the left, and I've got hydroxide on the right. So my water has actually lost an H+ ion. Therefore, we can define it as a Brønsted-Lowry acid. It's kind of lost or donated that proton to something else in the solution. So final Lewis structure again. Let's just have a look and work out exactly what's going on in my solution. There's some Lewis formulas for all of my different species. Let's add some curly arrows to show exactly what's occurred in this process. So first of all, yet again, my Brønsted-Lowry base has used a lone pair of electrons to take a proton from another species. And the second arrow, very similar to my first examples, shows those two electrons from the hydrogen-oxygen bond returning to the oxygen, therefore giving what's left over a negative charge. So key points, very similar again. The Brønsted-Lowry base has used a lone pair to accept an H+. The Brønsted-Lowry acid again must contain a hydrogen. In this case is my water, which actually contains 2 hydrogens. And a point we mentioned a moment ago, a solution of a Brønsted-Lowry base in water will always produce hydroxide ions, and that's going to be helpful later on in the unit. Final little point to mention, not all bases dissolve in water. So we have a little special extra term that we can use for bases that do dissolve in water, and that term is an alkali. So in this case, we could say that ammonia is both a base and also an alkali. Why? Well, because it first of all is accepting a proton, and secondly, what makes it an alkali is that it dissolves in water. That will probably do it for now, and hopefully this video is of some help.